continuing from solving the Pythagorean challenges, we're going to square the circle. But once you can, basically the second challenge is to draw any line segment and then to square it, or you get and then cube it and get that ratio. But if you draw the golden rectangle, and you get the phi ratio here, the Fibonacci sequence, you can also just label them and give them measurements. If we basically could call 1 at any segment, but if we call this 1 and break down the measurements, we get 1.618, and the thing is 6.188 and there. But Zeno's paradox, what point do we stop it? It's a choice. We could just sink the level up there. I chose to sink it once it would move down to the second decimal place. But it could continue to go, obviously, to infinity, being an irrational number. But the point is, where do the lines clash and reciprocate? But basically, once you have these numbers here, and combined with the knowledge of being able to trisect the angle, and you could take a pentagon and then trisect those, get a 30-sided angle. But now you have the 12 within the 10 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we close the circle and continue around 11, 12, 13, 14. Anyway, and we could go with the 12s, whatever count system you want to use. But you can convert now to square the circle, and these measurements here between between the 5 here, you see you got the one little Pythagorean triangle segmenting it once, then twice. You get another measurement to there of a third, and then you're peeking out based on into fifths, and it peaks out. But each one's giving you a triangle, which you can figure the area up, and then conversely. So you're looking for to close the vesica Pisces. But based on this, if it's a ratio of 5 to 6, giving you the 1.2 as the basis of numbers, I'm going to continue with that thought. But with this now, so if you take that and you can't square 1 in your calculator because you'd get in there, but if we can basically theoretically square that, cube it, now we can see is simply square this number, you get that, and transversely to that. But now once you have the cube, in essence, a perfect cube ratio of it, you can times that by pi, or excuse me, not by pi, but in essence, times it by the 1.2. If the theory is every linear line is equivalent to an arc of a circle of 1.2, now if we have a 2.61803339 times 1.2, we will actually get pi within almost 7 millionths of a decimal, 0.0000006 out 7. And it actually gets more approximate as you narrow it down. But then on that thought there, in essence, once you figured that out, I Googled it, and you could see what if anyone came up with the cube of the golden ratio times 1.2 and pi. And what came up was the Great Pyramid of Giza. What it is if you take the radius, someone figured, of the pyramid and call it a 1, and then it's a phi up to the peak there on the ratio, which happens to be that the height is 1.2. Now if you times 1 by 1, you get 1 still in the radius for the circumference in theory. But now you have 2.1680033 in essence for the slope. Now if the pyramid, the funny thing is if the pyramid was capped, it would actually be 1.27272727 repeating, but it's 1.2 without the cap, which gives you the 2.618 narrowed down to the golden ratio. It just happens to be that the pyramid rotates perfectly, as if you were standing on the equator and the Earth in 1/2 second rotates the exact amount of the side of the pyramid, and then a full second the full circumference of it. So at times perfectly. So in essence, they squared the circle. But now the 1.2, to prove that in numbers, the theory now, if you could prove the 1.2 is relevant to the arc, you'd also prove the Riemann hypothesis. And that's the next step.